are so powerful. Suddenly you see a 40% improvement in the quality. I mean, unbelievable improvement. So one major lesson that I learned is, and this is again always there is a discussion. In fact, once one business user was aggressive with me. He said, "You guys try to scare us with these sexy terms." I said, "No, trust me, that's not the case. We want to work with you. If we can use a linear model, we will go for that. Only problem is there are some times where you need to bring in these nonlinear, these complex models, and we are not given a choice. We have to build it, right? We have to make a system that recognizes faces, and you as a human are unable to tell you how you are able to recognize a face. Then why do you expect the model to be linear and tell you how it recognizes the face, or how it recognizes the punctuations or text semantics? So it's okay to let your teams or let your partners work on some of these advanced models, because what they are doing is to solve an extremely complex problem which cannot be solved, unfortunately, in simpler terms. So the third lesson that I want to tell is, the technology is at a place where you can elegantly solve some of these complex problems. Just because they don't have business understanding, work with them on how you develop a strong story, instead of discouraging them from going for any of these things. The last story that I want to share is what I learned recently while working with a manufacturing company. So this company had a nice, robust, complex machine that makes pipes, steel pipes. So it's called centrifugal casting. I'm saying the word here because this is a place where lots of manufacturing happens. So I'm assuming most of you are familiar with this, but it doesn't matter. Essentially they pour steel and out comes a nice pipe. Okay, so what they asked us is, can you improve my productivity? Okay, and what we said, okay, where is the scope for improving the productivity? We found there are three places where they were losing productivity. One is sometime the machine is down, so there is a downtime. Machine is not producing anything. Good, productivity loss. Even when the machine is up, it's not working at its 100% rating, or whatever the manufacturer said. If the manufacturer said it can produce 70 pipes an hour, it is only producing 66 pipes an hour. So even when it is up, it's not working at its 100% efficiency. Even when it is up and working, producing machines, pipes, some of them have faults. So there are three losses. There is a downtime, there is an efficiency, and there is a wastage or loss. So we went and it's a bit difficult to read from this curve. This is the theoretical efficiency. We took 7 months of data, made all this mathematics and computed 7 months of theoretical efficiency at every hour of the day. This is hour of the day and average over 7 months. These are the theoretical values. This is the loss because of downtime, this is the loss because of efficiency, and this is the loss because of wastage, or this thing. So we went with these graphs after 3 weeks of working. Then they came back and said, you know what, yeah, but we changed, we are not logging all our downtime, so this is not accurate. So why didn't you tell us that? We spent so much time doing that. Then we said, okay, we again took the data that they had and spent a week or week and a half, and then we said, you know what, machine 2 is behaving in its downtime very differently from machine 1 and 3. Great, there is something wrong with machine 2. Let's analyze that more. Said, yeah, we know this. You know what, machine 2 was having too many repairs, and we had a lot of problems, so ignore that data. Okay, 2 weeks lost. Then we went back and we started working again. And we said, you have some scheduled downtimes and you have some unscheduled downtimes, and there is no correlation between these two. If everything was going well, if you have a scheduled maintenance, then you don't expect an unscheduled maintenance after that because you took care of them. And there is no correlation. In fact, it's a negative correlation, which is what we expect, but near zero correlations. And we said, look, we found a breakthrough. Your scheduled and unscheduled can be improved, to make it. They said, yeah, we found that 3 months back, and we actually changed the complete scheduled maintenance structure. So please ignore the data that we gave from Jan to July and start from August data, which we will give now. This is after 2 months. So I said, why are we playing these mind games? I mean, what exactly is it that we want to accomplish in this project? Let's sit down and talk. And I had a session, and it is not intentional, but many a times extremely important things are because probably they are very obvious to you as a business user. Maybe stating it, articulating you may find it irrelevant. But the data scientists do not come with domain knowledge. They only know how to listen to the data, and they listen to whatever you give. You give them a nice, beautiful data, they can extract songs and music out of it. You give them noise, and then they are stuck with the noise, right? So it is, after we had the discussion, we realized several things that were important. So one major thing is the the head of the firm said, Murthy, I'm not interested in this 1 hour or 2 hour downtimes. I anyway know about them. What I'm interested in is this 1 minute downtime. This micro downtime, 30-second downtime, and they happen, and what is the impact of that? I don't get that view. Can you actually build it? So I looked at the data, and one of the things I went to him saying, good news, there are very few 1 minute downtimes in your data. You're great, you don't have to worry about it. He said, wow, great, I was worried that there are these 1 minute downtimes, and hence, this life is beautiful, happy. And then I went to the plant to work out some discrepancies of this. Then I looked at, in the 2 hours I spent in the plant, the machine was down at least 7 times. So I said, in the 7 months, if it was down only 2 or 3 times, or maybe I chose a particularly bad time, and it was accidental. 7 times it was down. Then I went and asked the operator, how come that's not reflected? He said, sir, when it is only 1 minute, we don't note it. I said, oh, thank you very much. And where is it noted? They said, oh, there is another data called idle time of the machine, which actually captures all that, but we didn't give you. Okay, man, okay, go back and then get that. Finally, we got that. And once we got that, in 3.5 weeks, we were able to look at this. It's a bit difficult to read. And by the way, while all these projects are real, now to keep the non-disclosure, to respect the privacy of the data, everything that I'm showing is dummy. It retains the contextual significance of the original case, but we never ever give out or display the data of the client in any context. So please take it only for the understanding and not for the actual exact values. Okay. So this is the same machine. Now what we found is in shift A, the unscheduled downtime is much higher than shift C. There's a much higher unscheduled downtime in shift A compared to shift C, but performance is more or less same. So we went and asked them, don't worry about actually unscheduled maintenance. What we found out is many a times they're overreacting. There are some problems that they're seeing in shift A, they're immediately jumping at it and repairing it, stopping the machine. There are same problems are ignored in shift C because it's night, engineers are not there, they're just letting the machine go. What we found is the productivity didn't change in both. Whether you are stopping and repairing, if you repaired, at least if the productivity went up, it meant some sense to repair it, else it didn't matter. So all this, and then we were able to find some scheduled and unscheduled that are happening together, so they could actually build a better maintenance structure. All these things happened in the next 4 weeks. So first 2.5 months we were playing games. Essentially, we will go back with some finding. They say, yeah, we didn't give you the data, caught you. And then we come back and we do something else, we didn't give this data. So it takes really, when you are designing a problem, spend a lot of time from a business perspective on building that integrity into the data. Think about, where all probably you're missing out on collections of the data, and tell that to the data scientists so that they at least know what they are hunting for. From your end, heuristics is one part, but the most important insight that the data scientist will not have that you will have is where you can trust your data and where you cannot. We can probably find out, but don't let us spend that time on finding out, validating the quality of the data unless you yourself don't have an idea. I don't know whether I can trust it or not. Then the project itself is, what part of the data you can trust, what is it that you cannot trust. But otherwise, spend as much time building the data integrity. Okay. The last two parts. What is so big about big data? Why is it important? Why is it important is probably already everyone knows. We are collecting a lot more data. First lesson is just because you're collecting a lot more data, it doesn't make it a big data problem. Maybe I can get the model built on 100,000 records, even if you have 1 billion records. Okay? So, but there are some cases where, like Google search, I want to find the nearest neighbor to this document. Let me search through the 1 billion records and identify the nearest neighbor. So there are some problems where I have to use the entire data, and it is genuinely a big data problem. But there are many times when I talk to the clients with the increased power to collect data, most clients are collecting a lot of data to solve a lot of problems. And because they have 800 terabyte data, they believe every problem is a big data problem. So spend time on whether you need the entire data and it's truly a big data problem, or it's a small data problem. More often than not, one of the first discussions that we at Soothsayer have with our clients is whether we really need it to be treated as a big data problem. Having said that, let us see the complexity of having let us say it's truly a big data problem. How do we go about solving? So currently we are working on a problem where there are 800 million records. What is big data? At a very simple level, if the data can be stored in a single computer, it's RAM. It is small data. If it requires multiple computers, it's big data. Let's agree on that definition. Okay. If this data can just go into one computer's RAM, we are dealing with a small data. Now that means that what is big data is changing year by year based on that Murphy's law. 20 years back, probably I could put 20 megabytes in the RAM. 10 years back, 100 or 500 gigabyte. Today, I think we are at 128 gig RAM is not a problem. We have servers that can handle. It will only get bigger. So today, any data that is less than 128 gig probably is small data, and more than 128 gig is big data. The question is, I have terabyte of data. I can't put it in a computer. What can I do? One approach, I can build a single supercomputer. Go to my boss and say, boss, allocate 20 million. Let's get a nice big server, let's put all terabyte of data. Great, the boss will say, okay, what will you do on it? I'll get you a customer pattern, great insight. Brilliant, what will you do after that? Oh, till the next quarter when we are doing the analysis, it just stays there. It looks good, pretty, and it will be there. It's very unlikely that it will fly with your boss, right? So now the other approach that people followed that was more sensible was, instead of going for a supercomputer that can have a 1 terabyte space, let me just take 100 small desktops. Let each one only handle 10 gigabytes. Okay, which is the approach that they followed. So instead of going for 1 mega super system, let me have 100 small systems and let me put 10 gigabytes of data in each thing. Then the first question that comes to our mind is, if I have 100 systems, what if one of them fails? I lose that analysis on the 10 gigabytes. What should I do? Logically, what will I do? I'll just back it up. That's it. And it's as simple as that. So what these guys did is, okay, when we are putting data in 100 computers, instead of storing, let me put in 200 computers. Let me use only 1/3 of the space for its own data. Let me back up 2 other computers' data in this. Okay, so each computer not only has its own data, but it has two other computers' data. So what is the chance that this will go down? Fine, there is a 1% chance. But when it goes down, I have it stored in two other computers. What is the chance that these two will go down together? Very unlikely. What is the chance that all three go down together? Gods have to be stacking against us. So, that's good enough. But, if you're really, really paranoid, you can back it up in 4 computers or 5 computers. So minimize the odds of you losing the data. So, one major paradigm or philosophy in big data is because I am distributing data in multiple computers, let me actually back it up well. And that's called Hadoop file system. That when you hear the word Hadoop, all they are doing is they're backing it up properly. Okay, there's nothing jazzy there. Now, I have data in 200 computers. I have a software. Should I get the data from the computer or should I send the software to the data? This is a 100-line or 1,000-line software which is 10 kilobytes. And the data there, even though it is split, still is a few megabytes or few gigabytes. Will I bring the elephant to the rabbit or will I send the rabbit to the elephant? Maybe sending the rabbit is better. So imagine the first case, I am looking at nearest transaction. So my program goes to the first computer and I'll map it to all computers, all my 200 computers. In each computer, it will find the nearest transaction, whether it will require prior authorization or not. In each computer, it had a nearest neighbor. Then I bring those 200 results and then I find nearest of those nearest neighbors. And then say, this is what you have to, the nearest of the nearest guys did not require a prior auth and hence this does not require prior authorization. So what am I doing? I am mapping my software to all 200 computers, getting 200 results and reducing them into one result. This is when your software engineers come and say they are using map-reduce paradigm. That's what they are doing. In big data, you keep hearing Hadoop and map-reduce. Hadoop is backing it up. MapReduce is sending your software to these 200 and bringing it and reducing it. Well, obviously, I'm not trying to trivialize the amount of engineering genius that went into it, but from a business user point of view, these are very logical things that you have to do. When you're dealing with such huge data, set it up and distribute it in multiple computers, send your program to all those computers, let them get results, bring it to one place, and then map it. The beauty is, thanks to Google's and Facebook's, some really complex big data engineering issues have been solved. And what is more beautiful, they have all been made open source. So today, for your organization to set up an analysis on 8 billion transactions is not scary. Everything is actually open source, if you look at it one way. It's a few months of, not few years, probably few weeks of work to set it up. And it's inexpensive because all the software is open source anyway. And I'll talk about my opinions on open source in a moment. But it's not a scary problem to handle this big data. In fact, for me, in my opinion, the scary problems are where there's not enough data. So, as James introduced, I studied material science. The first analytics problem that I worked on was predicting the failure of a nuclear reactor. In the entire last century, there were 6 leakages, 6 data points. Imagine 6 rows. And this is a place where I can't ask for more data. Can you experiment a few more leaks? I'm thankful to the God that there are only 6 rows. But imagine doing an analysis on 6 rows and 1,000 columns. What insights can I extract from such nano data? So nano data problems are much more challenging than big data problems. So if your organization is collecting a lot of data, it's really not a scary thing anymore. And there are some wonderful commercial and open source products that you can work with. Before I move to the last team building part of the presentation, I want to summarize here. It's a different way of solving complex problems. You can definitely have that to get some disruptive, highly insightful insights, which is very different from the way you normally solve an engineering problem. So that's why it's worthwhile and complementary. And to build that, this is something that I found in LinkedIn 3 days back. A successful data science is about right data, right models, gut feeling, and intuition. And I think this is where the business users are extremely important, in the data and gut feeling. And intuition is commonly shared by the data scientist and the business user. Models is where data scientist will play the important role. So I really like it, that those are the 4 successful ingredients. Now, the last section about building a data science center of excellence, particularly how to hire. You want to build a center in your organization, data science. I have to make an admission here. 90% of the job advertisements that I see, I won't get selected. It doesn't mean anything. It's crushing to ego. I think I can do some of those things, but I know the HR process is just too stringent. Advertisement reads like postgraduate degree in computer science or statistics with deep, excellent coding skills, deep understanding of domain, phenomenal communication skills, tall, dark, handsome, sensitive, humorous. I mean, you can ask for anything you want, but this is fictional. I mean, how will you ever find someone who knows so many things? You have to be realistic when you are building a data science team. There is a site called Kaggle that keeps conducting these Netflix-like competitions. And there they actually gave out and these are like rock solid data scientists, they gave their description of participants who have been winning these competitions. And majority of them are from computer science engineering, which means they can't talk well anyway. These guys, they don't even recognize you. Math and stat guys, they are in a different world. Interestingly, there are some social science guys. There are some philosophy, interestingly, law. People from all over the place actually come and they prove themselves as great data scientists. We are currently involved in building a product, and we, in the last year, implemented it in 2 billion-dollar companies and filed for 3 patents. So it's a very interesting, nice product. And the team that did that, the lead was a housewife who came to work after 10 years of not working, at home phase, and she went through a 1-year data science program. One of the programmers is a BS in metallurgy, who then didn't have any programming background. There is another one who is a BS in electrical engineering with 2 years of experience. None of the HR process, any of them would have been able to select. And I didn't go out of my way to put together a team that looked so weird. But it just happened that they were the best guys there. And why I took some of them is, before I go to showing how I built how we build the teams for any consulting engagement, I want to borrow a phenomenally good representation of the skill sets that you need in a team. The idea here is no single person will have all these skills. You have to put together teams. And this graphic very nicely represents what is required. There are hacking, this is programming skills. These are the domain expertise skills, and this is the math skill. Okay, ideally a data science team should have all. So I need a programmer, instead of looking for one person who has all these 3, I look for a 3-member team. But typically organizations sometimes make mistakes. They only take these 2. Then you have a machine learning guy. If they have programming and math skills, you have a machine learning team. You have math and just domain, you have traditional skills. Now this is my favorite. You put together a programmer and a domain expert and ask them to extract insights, that is the danger zone. The hackers can actually get some data and the business user can actually logically talk it out. And they say, you have to do this, your customers behave like this, and it happens so that they are not, and it's a disaster. So and the math and stat does have a role to play. So for me, ideally, I have a programmer, a math guy, and a domain expert. Plus, very importantly, I have a creative guy who can tell stories. Storytelling actually is a technical thing in data science. So it is not enough if you just solve the problem. I always find an extreme importance in actually being able to articulate that to non-practitioners is one of the key success ingredients of any successful data science project. So when you are putting together a team, either in-house or with a partner, figure out what skill sets that they should bring in, what you will bring in. Typically, this is something that you bring in. Your partner will then bring these two skills. But then one of these probably is the storyteller, otherwise have someone dedicated to interpreting those results, making sense out of them purely from a layman's perspective. That's an extremely important step in any successful data science projects. So a good programmer, good math, good domain expert, business consultant, storyteller, and sometimes for extremely complex problems you need probably a much more experienced data science guy. So my experience, unlike the complex software projects, data science projects, I feel I start getting uncomfortable if the project extends beyond 3 months. If we do not get decent insights in the first 12 weeks, I'm not saying completion of the project, but if we start working on a data and if we don't get an insight in the first 12 weeks, it's scary. You can demand design your work such that you have very early milestones. Every 3 months, what are the milestones? It can be practiced in a very agile way. Unlike, I feel very uncomfortable when we sit and talk about, next 1 year, let's just plan and architect and test waterfall model. So 15th month is when we'll give the first insight. I don't think that's a good practice at all. Whether you are engaging in-house or externally, every 3 months is a very good point to look at, okay, what has been accomplished. You should be able to accomplish substantial things and with a 3-member team. And that's the point. You may have billions of rows that require 100 people, but first get the quick wins. Put a 3-member team that can program, do math, and there is a domain expert. They work together. They look at that subset of data, ask a question, try to find an answer. You should